Let's get started. Today we're talking about Chapter 6, Model Training. It is, we're closing to, we're getting close to like 1/3 of this class. And Chapter 6 is about model training. So we'll be talking more about training the model and how that can be fit into the pipeline. And the next one is model analysis and validation. So after the next chapter, we'll be pretty much done in terms of, looking at all the components and stuff. So then we'll be basically just either dealing with model deployments, or serving, or just orchestrating the pipelines, and or basically looking to scikit-learn with workshops and stuff. So the basic components will be done next chapter, and I think in as you can see or feel, the coding requirements of this class pretty much ramps up from here, in terms of model analysis, model training, model analysis, and then, building the orchestration pipeline and stuff. So, so definitely get ready in terms of that. So let's get started in terms of reading. Let's see, maybe we'll spend around 50 minutes to read for the next 50 minutes, chapter 6. And Mash, if you don't mind setting the timer till 10:30 p.m. EST or 7:30 p.m. PST, that'd be great.
Sure.
All right, I'll talk to you guys in 50 minutes.
Time's up, folks. How are we doing?
All right. Cool. Is everyone done with readings? Well, I take the silence as yes, or maybe no. Maybe there was too much reading within 50 minutes. I certainly spent a little more than 50 minutes, I would say, on the reading. But it is very interesting, the way how the author chose to embed the text features. And it seems like that is, something that uh, nowadays you would see more and more in terms of, being able to vectorize or represent your categorical features or text features with embeddings. So, and the author, used that as one way to train the model or feature engineer. So let me share my screen. I actually just finished training this model, which is nice, and I tuned it down. It was taking me 1 hour, but I lowered the number of steps to from 5,000 to 50,000 to 5,000.
And check, did you run it on your local machine?
Yeah. So, and I was just testing it. Obviously, I should have probably put it on, a GPU, which I don't have on my local machine. But it is a fair amount of parameters because it was calling universal encoding model, I believe, from TensorFlow Hub. So it is. I'm sure it's a sizable model. As you can see, how many parameters there are. And let me see if this is still running. It probably still is saving or something. And accuracy kind of peaked out, and it was going up very slowly, after like 2-3 minutes. So with 5,000 steps, I was doing like basically, okay, I got validation binary accuracy is 77%. Okay. And I think this data set is not so imbalanced, so the binary accuracy might not be too off. Uh, that's that, but I should have probably used, better metrics such as AUC, ROC scores. And I was just doing a test on the local machine, and to be able to run this data sets, the consumer complaints, that's what we've been dealing with, and trying out the very interesting feature engineering methods as well. So, and I was trying to use 4 workers. I don't know if I think it might have worked as I passed in multiprocessing. So instead of doing 1 worker, I just used 4 workers because I have 4. It's a 4-core CPU, as most of your laptops would have. So that's that. I already pushed. So one note is that this pipeline or this line of code, local DAG runner, does not run in IPy kernel, so you wouldn't be able to run this, with a shift enter from this magic command. It would run in Jupyter Notebook. It just doesn't run in VS Codes with this line of code. Everything else runs. You just have to run this in the terminal, and you just press Command B and running through this entire .py file. Then you should be able to run this and train your model. So, and once you're done with this, you should have, I saved it under the folder called pipeline root. I'm not committing this, but you should have everything, all the way from CSV example gen to trainer. Yeah, so that's that. And I don't know why it's still running, but it seems like it is still running. Okay, so I had 77.67%. Perhaps we can do better in some other ways, but I haven't. Well, also we haven't fine-tuned the model. And the tuner component is a component that just came out. If you read the book carefully, even when the book was being finalized, the tuner components, I think it was just about to come out or something like that. So that's why, again, this topic is fairly new, as things come out even while the author was writing the book. That's how, it's also how fast the field is emerging and evolving. Okay, so without further delay, let's dive into the book or the chapter. Model training is the fourth component of the entire process. We went through data ingestion, data validation, data pre-processing. Then now we're focusing on model training. The next chapter, again, we will talk about model analysis and validation, looking at different ways to evaluate your model within the pipeline. Then you push it, right? You push it or serve it somewhere. And we'll talk about how you can do that on AI platform or GCP's AI platform, and serving or storing your models on Google Cloud Storage, right? Then serving your model from AI platform and with a API endpoint, which I kind of demo that through Hands-on ML's chapter 19, but of course we'll do that here as well in a way that's represented by a pipeline. So cool. Then we'll basically dive into all the orchestration tools, mainly on Kubeflow and Airflow. Then of course there are a couple other workshops with scikit-learn as well. So all right. Yes, defining the model for our example project. Since this chapter is about modeling or building the model, we want to try to define what our model is. And in this case scenario, we're talking about transfer learning from a pre-trained model, which is our universal. Let me pull this up. Should be this one, tfhub.dev, universal sentence encoder 4. So basically, this is a pre-trained model, encoder of greater than word length text trained on a variety of data. It's on V4 right now. The universal sentence encoder encodes text into high dimensional vectors that can be used for text classification, semantic similarity, clustering, and other natural language tasks. So in this case, we're using this for classification, right? But not for text classification, but just for consumer complaint classification. The model is trained and optimized for greater than word length text, such as sentences, phrases, or short paragraphs. It is trained on a variety of data sources and a variety of tasks with the aim of dynamically accommodating a wide variety of natural language understanding tasks. The input is variable length English text, and the output is 512 dimensional vector. We apply this model to the So we're talking about 512 here, right? Then we feed that into 255, 6, 64, 16. So gradually kind of, lowering the number of units we're using. And we apply this model to the STS benchmark for semantic similarity, and the results can be seen in the example notebook made available. The universal sentence encoder model is trained with a deep average network encoder. Okay, so if you want to know more about this, please dig into the TF Hubs link. Let me share that in the chat. So it's just one way of encoding your text, or sentence text, longer than words. So it's not word embedding, but sentence, more so like sentence embedding. Okay, and all right, and this is what the model architecture looks like. Okay, and the feature in our model include the financial product, the company's response, the U.S. state, and the consumer complaint narrative. Our model is inspired by the wide and deep model architecture, with the addition of the universal sentence encoder from TensorFlow Hub to encode the free text feature and consumer complaint narrative. So the narrative could be, a bunch of sentences, basically. That's why we're using universal sentence encoder to embed that, which is cool. And the way how it's done is basically the narrative feature gets inputted here. And we have a keras layer, we reshape it, dense layer, dense layer, dense layer. And then at this level, we concatenate with all the other features. And I believe this is probably what it's called, wide and deep model architecture. Let's see what it is. Wide and deep learning better together with TensorFlow. Okay. Anyone's familiar with this paper? Has anyone heard of this? Is anyone familiar with this?
Yep, this was with respect to, I think so, the determining the number of features with respect to the over parameterization. How many categorical features, like they have alluded to in this post. Yeah, and what's the difference actually between the how do I say it, the depth and the width of the neural networks, and how do we actually determine what which is better? They gave empirical evidence as to the various, how do I say it, the various properties of scalability too. So yeah.
Cool. Someone raised hands. Philip, you want to speak? Philip, do you want to unmute yourself and speak, or you want to text? No mic. Okay. I mean, if you want to just text or text in the, or type in the chats, that'd be great as well. Great. Thank you, Mayank. Okay. I haven't dig too much into this, but it seems like that's what's going on. This is basically, having the inputs all together, right? And concatenating them, and feeding that into dense layer of 16 units, I believe. Then you concatenating them, right? So we're talking about we're talking about 16 by however many dimensions the input feature is. The input shape is well, depending on the batch that we use, but 16 units, right? So the columns are all 16, so then we can concatenate them together, and then feed that into an output layer of 1 unit with sigmoid activation, obviously, because we're just dealing with 2 classes. Okay. Anyone has questions on this model architecture? Okay, so for the features, we're dealing with one-hot features. So for some of them, we're just basically dealing with, we're just one-hot encoding them, and some of them we're just bucketize them, and some of them we, I guess one of the features is embedded with universal sentence encoder, and that is I guess appended into the input text list. Everything else is under the input features list. And then eventually you call the Keras model, you have the inputs, outputs, then you compile the model with the optimizer of Atom and learning rate of 0.001, binary cross entropy is loss function, and your binary accuracy and true positive. Obviously, we can pass in more, such as AUC, ROC scores, and other metrics that we typically use for classification models. Okay, so the Tfx Trainer Component. This component handles the training steps in our pipeline and requires the following inputs: the previously generated data schema generated by the data validation step in chapter 4. So chapter 4, one second. Chapter 4 is the data the data validation chapter, and the transform data in its pre-processing graph, the transformation graph from chapter 5 that we talked about. And training parameters, the number of training steps, a module file containing a run fn function. So this is similar to pre-processing fn, if you recall what we did last class. It's also something that trainer component will detect, and it has to be named this way. So, and if you look into what we had, well, let me open up the class GitHub just so everyone's clear where it is. So this is under base pipeline. Okay, this pipeline is under base pipeline, and it's under the folder of pipelines. That's where you find the file called base pipeline. This is where you see all the components. Okay, and under module is where you see all these functions. And module is underneath the components folder of the class GitHub. Not our practice GitHub. But the books GitHub. Okay. Someone asked Arjuna asked, when you cannot use this dense, can you explain this a bit? So dense layer, just like linear, well, just like a, a layer with product, some product operations, right? And so sometimes you don't have, you don't need dense layers, or you don't want to use dense layers. Sometimes you could have residual blocks, such as ResNets, right? So you might not use dense layers in that case. So depending on what tasks you're trying to solve, you might not use dense layers. But typically, I would say dense layer is something that we would use in tabular classification data sets. Okay. So, and as you can see from this module.py file, we have all these helper functions, okay? And we also have this preprocessing FN, like we said, and the get model function that allows us to get the model from Keras, or the compiled model that we can customize right here. And then we also have the input FN that we feed into the run FN. The run FN is the function that Tfx Trainer will call, and this will be passed into the trainer component. Okay. And as you can see, run FN takes in the input function, and it generates the training data set and evaluation data set that way. And you also have a callback on TensorFlow, Tensorboard, I'm sorry. And so that you can access the Tensorboard this way as well. And once you run through this, right? So the metrics will be stored somewhere. And if you run the Tensorboard commands, you'll be able to view your how your model has performed as well. And your signature, right? This is where you put in some metadata for your model, and you save your model with this line of code, model.save. Okay. Now, this is somewhat a little bit, I guess it was not very easy to understand some of these arguments, fnrx.trim files, tf transform outputs. Well, that's relatively easy because we had that from our last class. And from that, we generate, our training data sets and evaluation data sets. And we also gzip, we also have a gzip reader FN, compression type gzip, and we also have this tf.data, tf record data sets that we pass in as a reader to this. And we also have a batch size of 32, okay? So that is, I guess that is one of the dimensions of the data inputs. So I guess, since this is a, I'm thinking whether this is 32 by 512. I'm guessing that's the case because the base pipeline says Oh, it was the module file. Yes. So I guess 32 by 512 for the embedding. And I suspect for the other features, it's probably 32 by 16. That's what I'm guessing. If anyone else has a different thought, let me know. Okay, then eventually you're able to concatenate these two matrix together, then feed that into this the one last dense layer with sigmoid activation. Okay, and we compile the model, train the model. Training steps versus epochs. Do we need to explain that? Is everyone familiar with those basic concepts of ML training? Steps versus epochs. Okay, a training step is when the model is trained on a single batch of data. And in this case, we're doing mini batch grading updates. And the benefit of using steps rather than epochs is that we can train or validate models with large data sets and only use a fraction of the data. At the same time, if you want to loop over the training data sets multiple times during training, you can increase the step size to a multiple of the available samples. Once the model training is complete, the next step is export the training model. We'll have a detailed discussion about exporting models in chapter 8. And this is a model exports. We'll talk more about model signatures in chapter 8 as well. And we're saving the model in TensorFlow's saved model format. Okay, this is TensorFlow's own model formats. And we define a model signature based on graph generated by example 6-4 function. Okay, this is example 6-4. Okay, so that's calling the function, you're passing the model, and the transform output, get concrete function, TensorFlow spec, and then you save the model right here in this directory. Okay, I didn't quite, this was something that I had a little bit difficulty understanding in terms of how this was done and passed into this signature. So this is applying the pre-processing graph to model inputs. And we have a tf.function decorator. It's basically kind of converting this entire function into TensorFlow graph. Then eventually you run the trainer component, which I did in my little experiments. It was using 1,000 here, but I guess the original or the script here had 50,000. And this is probably where you want to be, I guess, in the end, if you are, seriously training this model and fine tune them, right? So, and that's probably where you can get to, in the end, maybe 80 plus, 85+%. Okay, so this is where you can also pass in a bunch of other metrics as well, AUC metrics. But that will be done in the next chapter, model evaluation. Okay, this is talking about a safe model outside the pipeline. I mean, that's something I'm not going to cover too much. You can absolutely do that. But usually, since we're covering the topic of pipeline, we're just going to save it within the pipeline. Okay, and this is pretty cool. I always thought being able to kind of, incorporate tensor boards into your interactive pipeline is something very hands-on, handy. And you can kind of view your accuracy. And this is where I got, right, too, as well. I guess not too much higher, somewhat similar, between 76% and 77% binary accuracy. And the way how you can do that is actually fairly straightforward. It's basically served as a callback where you can pass in right here when you call model.fit. And let's see. Here's pipeline. It's in the module.pop file. Model.fit. Right here. So callbacks equals callbacks, and this is TensorBoard callback. And you just need a log directory. Make sure you when you run your model, you have a log directory as well. And then you define your TensorBoard callback as tf.characters.callbacks.tensorboard. You pass in the log directory, update frequency per batch. Then you pass into that as a list, and then feed that into the callbacks parameter of model.fit function. Okay, then you just basically call this commands, and then you can just view your TensorBoard visualization. So. Okay, so the book also talks about different distribution strategies. So because some models just can't be adequately trained on a single GPU, and GPU does have its own memory as well. So not just CPU has memory, but GPU has memory as well. And so if your model can't really fit into your GPU memory, what are you going to do, right? So TFX or TensorFlow provides different distribution strategies to train your models distributively on multiple GPUs on one single cluster of computing resources, or perhaps on multiple clusters, right? So there are different strategies, and there's synchronous strategy, there's asynchronous strategy for training as well. And it's defined, the synchronous strategy is defined as all training workers train with different slices of training data synchronously, and then aggregate the gradients from all workers before updating the model right here. Okay, and the asynchronous strategies train models independently with the entire data set on different workers. Okay, and each worker updates the gradients of the model asynchronously without waiting for the other workers to finish. So typically synchronous strategies are coordinated via all reduced operations, and asynchronous strategies through a hyperparameter server architecture. So mirror strategy is something that you basically train on a single computer or single node with multiple GPUs. Okay, and your machine learning model fits into the GPU memory, assuming. Central store strategy, the variables in this strategy are mirrored across all GPUs. Instead, they're stored in the GPU's memory and then copied into the assigned GPU to execute the relevant operations. That's a good strategy for distributing your training when you train on a single node with multiple GPUs and you complete model does not fit into the memory of a single GPU. Multi-worker mirror strategy, it's an option if one node isn't enough for your model training, meaning you need multiple nodes, right? Multiple nodes of multiple GPUs. And there's TPU strategy, Google Cloud's TPU, utilizing that. There's parameter server strategy, one device strategy. You guys read through this, but you know, this is something that you can actually call. So it's not just talks, right? We're not just talking. We're actually calling the function that's called mirror strategy. And I believe the book also said when the book was coming out, mirror strategy, yes, mirror strategy is only supported by Tfx Trainer at the time when the book was coming out. And but other strategies will be made accessible via the trainer component in the second half of 2020. We've already passed 2020. The book came out late 2020. So I guess at the time when the book is actually published, possibly a lot of these strategies are already available. And let's take a look at, I guess, Tfx distribute trainer creation strategies. Okay, that is perhaps not Tfx Trainer. All right, was not able to find it with a quick search. Let's keep going, I guess. But this is how you can call it, tf.distribute mirror strategy. Okay, GPU 0, GPU 1, GPU 2, I guess, depending on, how many GPUs you have, you can just pass in that. And it will, I guess, in default, it will use all available GPUs in an instance to train. Model tuning, hyperparameter tuning, and these will be covered more under Tfx Tuner. Okay, I think Tfx Tuner was, again, has not been made available when the book was being talked about. Let's look at that. It's Tuner. This is Tfx Tuner pipeline component. Tuner component tunes the hyperparameters for the model. It utilizes a lot on the Keras Tuner API for tuning hyperparameters. Tuner takes tf.examples used for training and eval, a user-provided module file that defines the tuning logic, including model definition, hyperparameter, search space, objective, and so on. Proof above the definition of training args and eval args. Okay, so we have our trainer here, and we have our tuner right here. Cool. It's good that we have a good example of what tuner looks like. In this function, you define both the model and hyperparameter search spaces and choose the objectives and algorithm for tuning. The tuner component takes this module code as input, tunes the hyperparameters, and emits the best results. Trainer can take tuner's output hyperparameters as input and utilize them in its user module code. The pipeline definition looks like this. So the tuner is right here. And where is that being fed into? Let's take a look at. So tuner. Right here. Hyperparameters equals to tuner.outputs best hyperparameters. And this basically goes into this. And what this has is, oh, okay, so your module file now should have a tuner FN. Okay, so beyond pre-processing FN and run FN, let's have a tuner FN. And then we can all pass in one module file. And also takes in the transform.outputs and the graph and this as well. So your tuner FN basically is defined right here. Okay. Then you pass that into the trainer, right? So very cool. Cool. Great. Thank you, Mayank, for the cut-ups and the links.
Quick question. So would this be conditional on just running on GCP? This is just TensorFlow. So if you were to run this, in theory, you can run this on any cloud platform, right? This is cloud agnostic. It's just TensorFlow with the right TensorFlow component. In theory, we should have been able to run this on our local machines.
Yeah,
or
exactly.
Linux-based, a Linux machine with a GPU attached or whatever. It should have just worked, right?
Yeah, exactly. It doesn't necessarily need GPUs. That's what it is.
That's the other thing. Yeah.
And it's platform. So TFX is platform agnostic. It's not framework agnostic because it has to use TensorFlow. Right. But at least you can deploy this on anywhere pretty much.
And that's where the distribution strategy comes in to figure out, like, are you going to run pieces of the model, pieces of the training model across different
nodes and clusters,
and so on. Yeah.
Exactly. So if you have a huge ML model or DL model that you need to train on, then you want to make sure you allocate your resources as efficiently as possible and as distributively as possible, right, across all your nodes and clusters. Okay, so that is it in terms of this chapter. We want to, as we have been saying, basically, we always want to incorporate TensorFlow's own tutorial. So we got one extra notebook and that we're going to run through very quickly. I'm going to share this link with you guys. very quickly, and Mash is going to take over. And for the next 15 minutes or so, we're going to spend time on this TFX Keras components tutorial. It's just, this is also end-to-end pipeline, but focusing on another different data sets. It's a more realistic or real-world data set, just like the data set that we currently tackle, but it's more real-world than the Penguin data set we talked about, right? And this is basically on the tax fares data sets or taxi trips data sets released by the city of Chicago. So it's definitely real world and somewhat messy and not very clean, I guess. So, and it is an end-to-end pipeline run through by Google's own tutorial. So it is something that, very cool to look at as well. And it definitely ties nicely into this current chapter, which is model training. So it has a trainer components as well. Let me look at this right here. So has the transform names, input FN, build Keras model, wide and deep classifier again, right? Wide and deep classifier with tabular data sets and run FN. Okay, Mash, do you want to take over?
Sure thing.
All right.
Let me share a screen. Zoom. I'm just going to share. All right. Can you guys, am I sharing screen yet? No, I'm not.
Yep,
Yeah, you are.
You are.
All right, so let's reconnect. So what I did was take that that example that Wencheng just mentioned. It's, if you follow along to the TFX tutorials, under the interactive tutorials, it's the first one, the TF2 Keras. And this is the one that does the tax. All I did was I ran this a few different ways, saved it locally to my own Google Drive Colab notebook. So let's go ahead and do just that. The first part is run a few packages. So just to get past the deprecation thing, and then let's redo the runtime, make sure I've got a GPU, and restart the runtime. Restart runtime. And let's see what we get. And voila, I won the jackpot. I got a Tesla T4 GPU, a nice $2,500 machine. And
very nice.
Yeah, and so when you run this, it runs fast enough that you should be able to, guess not. I had to do the whole thing all over again when I reconnected.
Just a quick question, Mash.
Yes,
do we just, I've never looked at, what kind of machines I got from Colab.
Mhm.
Do they just like randomly assign machines to, each Colab instance or something like
Yes,
that?
it is random. It is
Okay.
very random. I mean, and you get the wide range. Sometimes you'll get a T4, sometimes you'll get an A6, sometimes
Nice.
you get some pretty good ones. Other times you might get a very bad GPU.
Yeah.
That has happened. And
Cool.
these are even in live sessions. Mayank, when you and I were in the NVIDIA session, we made a point about that too, right?
Yep.
Some people were able to get some pretty good GPUs, and even the instructor got the crappy one while they were live demoing. But let's see what we get again. Yeah, still got a Tesla T4. Maybe it's just the time. So now it should run with no problems. Yeah. And we've got the right version controls. So just the first thing, in Colab, because Colab runs in a certain temp space environment, you have to set all of the pipeline paths. Wensheng mentioned this very briefly at the very beginning, just setting up the pipeline, but you need these paths. So this is going to be necessary because we're going to be downloading the data file, putting it in a certain place where the models are going to be saved in a certain place, enable logging, so we can see it. So let's go ahead and get this particular data file. This was run. And now it'll download it fairly quickly, and it did. So let's take a look at this data file. I added a couple of additional bash commands just because I wanted to see a little bit more about this data file. I want to see how long it is. It's over 15,000 rows. And there are different bash commands where you can see what's the longest line. It's whatever it is. That doesn't by itself mean much, but you've got this data file. And in this, what we're going to be looking for is we're going to build a model that predicts, where is it? Tips. Come on. Right.
It's the last column.
Is it the last column? Yeah, it is the last column. Tips. We're not going to predict fares. We're going to predict tips using fares and all of these additional data points, such as where latitude, longitude being picked up, and so on. That's what this data set is. So let's go ahead and begin very quickly. The first thing you got to do is set up the interactive context. And then if you remember, example gen is the first you've got to set up. And you can, example gen takes in these different artifacts. And then we'll get in. And so let's start pulling in, for example gen. You're basically creating that, what to me seems like a schema file. It's in JSON. And this is what it looks like. You're doing this. Wensheng, help me out here. This step is reading in that CSV file and doing the split train initially, as well as just setting it up as a TF record data set. What you had said was TensorFlow Extended's in native data set format, right?
Yep.
Okay. And then just take a look at what that is. And then you set up statistics gen. And that helps you, and then run against, with context to get the statistics on the data set. And this is like pandas profiling. Can begin to see everything. And here you go in tips. Clearly, we're going to need to do some pre-processing because 68.91% has zeros.
Well, that just means 70% people didn't tip.
Yeah, pretty shitty, if you ask me. But anyway, that's in the training set, and then of course the eval set, roughly similar. But these are things that you do have to kind of look for. There should be a max too, like maximum tip, which was nice, $20, and so on. But use the schema gen and kick that off to now begin to see here are the different schema types for the inputs and so on. And you can, that's set up. And of course the outputs. Once we have that, kick it off. And when you call it the schema via context, you get like, this is the input file. And so you go from there. The next step is the example validator. Same thing as earlier. And you can, when you do a context show on the validation, on the validator, you Here you have it, no anomaly. It does, Validator looks for specific anomalies. Now, what's unusual to me is Validator was run with no anomalies. This is what we'd expect, since this is the first data set we've analyzed and the schema is tailored to it. However, you should review the schema to look for anything unexpected. I would have thought this would have picked up some of those anomalies like the zeros and so on. But oddly enough, it does not here. And so here is the transform, and this is where it will transform the categorical features and so on. So define the taxi concept module file as this, and this is just to name it. And here is that, it'll save that as a .py file. So now that .py file is done, and we can actually call it and read it. When you open that saved file, it looks exactly as what was input here in the right file. Obviously, that is exactly what you'd expect. Same thing you do with the pre-processing FN, as Wenchang defined. Here's where you set up the pre-processing FN function over here. Pre-processing FN sets up blank dictionary for outputs and goes through the individual steps of, here's what you do with dense float feature keys, vocab features, et cetera, without necessarily, is there any, do you guys need to walk through any of this function?
We can probably just browse through this for the sake of time. Yeah.
Well, it is as you see. When you've got that and does that, and then return this outputs dictionary.
Mm-hmm.
And so this is where you have to do whatever standard pre-processing you have to do, get saved here. Same thing with things like fill in the missing features, et cetera, run that, and it's also saved exactly as you'd expect. So all of those steps, the pre-processing, the transformations, are saved as Python files. So when you then kick this off, when you kick off the transform function, it knows what to look for. And using that saved Python file, it does, here it goes. It's off to the races.
Yep.
Now, is this where Wenchang, this transform function being run, is this the runner? Yes, it is. I just answered my own question. Context run.
Yeah.
Runner.
Yeah, because what context.run is doing is basically it's trying to run every step of the way. Whereas if we don't do that, it will only be run at the end when we call the local dagger or airflow dagger, whatever dagger that you use to orchestrate the pipeline, basically. And then it will run just like what it's doing now. But what context run does is just basically help you to run that step immediately right now with the help of an interactive notebook.
Yep.
Yep.
Thank you, Wenchang. And so from there, here are the outputs, the transform outputs. Once we have that, transform outputs can also be set up into a graph artifact, as so. Here is the graph artifact. I wonder if we could see the graph artifact. Looking at it, at these points, I don't see how, but moving on. Here's the 3 transformed examples. You can kind of see what those new values have been set as. When that's run, then we create the trainer. The trainer is, here's the code for it, which basically is call the right components that you need, do the necessary imports, and define the features that's needed, including the keys, your dependent variables, independent variables, blah, blah, blah.
Gosh,
Yes.
sorry. So,
Mhm.
so the previous block is how you actually look at the data, actually, because you asked the question how we can look at the transformed metadata. That is exactly how you look at it, the previous block.
This
right
block.
here. Yeah.
Okay. Scroll up a little bit. This one, so this would be the first row, right?
Mm-hmm. First three records and decode them. So it says right here, if you scroll a little bit above.
Yep, right here, iterate over the first three records.
Yeah. Yeah, exactly. So this is how you look at the transformed examples. Yeah.
Okay. Got it. So you can look at the first three records or a specific record and so on.
Mm-hmm.
All right. Very good. Thank you. And then let's define the trainer. Trainer writes that to trainer file. And so exactly as we would expect.
Yeah, so this model, I don't think this model utilized anything fancy like, universal sentence encoder. It was just basically, I think it was just basically encoding them.
Missing variables,
Yeah.
values, and so on.
Yeah, I don't think it was using any embeddings to engineer the features and train the embeddings either. So, yeah.
And so now is when we go off to the races. Kick the trainer off and it starts running. And this, I presume, is the part that if we were to run this on our local machines, this is where we need the GPU. And it doesn't take too long, as you can see, to finish.
Mm-hmm.
And as this runs, following this, the next steps would be use Tensorboard to take a look at the model. If we were to kick this off, this is a saved file, but let the model finish. We're about halfway there.
Cool. It's doing relatively well.
Mm-hmm.
But with the binary accuracy, I guess, it's 70%. So we might want to investigate other metrics beyond binary accuracy.
Yeah.
So
now this should be a regression model. That was the other thing. Why use a binary accuracy for tips being a regression model? It isn't tips, yes, paid or not. It's tips and what is the value of the tips. So what would be the usefulness of a binary accuracy in that case?
Well, I think it is trying to investigate what factors affected people's tipping behavior, whether people just tipped or not. I don't think it was trying to see
what the value of the tip was.
Yeah, exactly.
Mm-hmm. Okay. And so this kicks it off, and here's Tensorboard launching. Here we go. And here it is. By batches and so on. If we go to graphs, and here's where you can see this is not a simple architecture.
Yep.
Wow.
Yeah, not a simple architecture at all.
That is cool.
Mm-hmm. And then finally onto the evaluator. define the evaluator, which takes the model specs. And this is where it uses that TensorFlow evaluator TFMA that we imported early on. That was one of the components that for whatever reason, I could not get it to run on my local machine. It only worked on Google Colab. This TFMA is what failed for me, my local machine, just FYI.
Okay.
And so from there, once it runs that, we'll take a look at the outputs. And here are the outputs individually. And so we could, again, do the context show on those evaluation outputs, and it presents it in a more graphical way. Want to do binary accuracy, sort by loss, and so on.
So what you want to do is, as you can see, or as you know, as you might have imagined, this is something to be put on the dashboard, right? So once you operationalize your entire pipeline or ML pipeline, then every single run of your ML model or every single run of your pipeline should output some visualization and statistics that would be basically shown on the dashboards, right? And Kubeflow pipelines, I believe, offers some sort of dashboards or at least some visualization of the graph. And also you can build your own customized ML ops platform, or you could use something like, I believe there are platforms out there like Clear ML. I don't know if they offer something like this, but you can try to build a dashboard that just takes in TFMA, right? Visualization on your dashboard. In this way, every single run of your ML pipeline will be able to kind of be, I guess, presented in a visualized format, so that you can compare and analyze every single run and investigate further. So there is definitely a place for visualization like this. But of course, in the production environment, that's not where you put these visualization and exploratory data analysis, for. So.
Yep. And then perhaps put code in a way that if your model results fall below a certain threshold, it brings off some alerts.
Exactly.
That's why you'd want them in a dashboard. But then a lot of times people won't look at a dashboard routinely, so create alerts.
Yeah, exactly. But as you operationalize your platform more, then as a data scientist or data science engineer, sometimes you can just sit there and be like, hey, today, every model is running fine. I guess no, there's nothing for me to fix, right? Because I can see, all the models are running fine. So, or maybe tomorrow it could be like, hey, this model just this model's accuracy just dropped way below the threshold. Let me look into what's going on here, right? So that's something for data scientists and perhaps DevOps or data ops engineers to work together to solve problems like that. So.
Yeah. So finally, we get to the pusher, the part of the pipeline where you push that and export the model. And so here it is, context run pusher. You can see the outputs for the pusher, which basically says, this is a model. The artifact is a model. Did you give it a name? Well, name was pushed model, blah, blah, blah. Here's where it's located. version control, custom properties like the TFX version, you could probably put a model version number or so on. And so that model, if you look to where it's saved, here it is.
Yep. I believe that we also have pruning and quantization steps here too. And we can model our pipelines after this step to through a couple of components like Onyx to convert that into how do I say it mm, um, a model that has to be distributed across constrained devices too, and perform additional validations and distribution and all that distribution shifts and all that downstream tasks that can be done before putting it into production. Or if I say I have to deploy it across Android and iOS, then we can have a custom pipeline that transfers this to via Onyx, or we can use Apple's and Android's native TensorFlow conversion tools like TF-Lite and stuff to push it down there. So yeah, that is additional.
The bottom line, these pipelines and the way the pipelines are implemented are going to be unique to the context that you use it for what use cases you're using it for, to the company that you work for. So I can easily imagine an industrial company that works with maybe images or something, they're using a lot of deep learning, TensorFlow framework. They'll have their own implementation. It'll follow this generic template structure for the pipeline, or it could be a little different. Or as we started on chapter 1, Uber has Michelangelo. That follows the same similar template, but their components are uniquely developed by Uber. Airbnb has same pipeline structure, similar pipeline structure, I'm sorry, but it's uniquely Airbnb with their own developed and coded components.
No, totally agree, because they develop their own platforms with respect to the customizations that they need for their own engineering practices. Yeah.
Yep. Yes.
Okay. Well, that's pretty much it. All right. Any other questions before we close this session? I think things are getting more and more interesting, and we're getting more and more towards something that's cool and, just like also very productive and very practical as well, right? Something that we can absolutely use for our other projects or for our projects at work as well.
Yep. Since we've taken you guys a little over time, can I at least share one little thing? Coursera, we all know and love Andrew Ng. Many of us started learning so much of machine learning from him. In fact, his first Coursera course when he founded Coursera. Well, he's launched a new course
I just saw that today.
Production. Yep, you got the same email I did. And here it is.
Yep.
And if you look at the syllabus, it's about 10 hours to complete. So if you guys can spend time and just breeze through it, this is Andrew Ng himself talking about and teaching what we just covered.
Very nice. Cool. I'm sure he teaches better than I do. Not many people can teach. Not many people can teach as well as Andrew, and that is absolutely for sure. I've benefited so much from his teachings and his videos. It's really, really good. Yeah.
All right. That's it for me. Thank you.
All right. Thank you, Mash. Really appreciate it. On that end, thank you everyone as well. Have a good night.
Oh, thanks everyone. Stay safe and Eid. Happy Eid.
Thank you.
Yes.
Thank you, Mayank.
Thank you, Mayank. Stay safe as well.
Yeah. Please stay safe, and I hope the best for everyone and your family as well.